two parts. The first short part is an award presentation for the J. Modi Memorial Award, and the second part is a distinguished lecture. But let's start first with a review of Prime J. Modi, who was with us. He started in Drexel in 2005, and he was coming to us from USC and CMU. In a very short time, he established himself as one of our best teachers and won a number of research awards, again, in a very short time, including the NSF Career Award and the Top 10 Young AI Researchers Award from IEEE. He was a tremendous asset to our department, and so this speaker series is a way to honor his memory and honor some of also the outstanding work that's being done in this area and throughout computer science. We're also honored to have Jay's father with us here today, Jayanti, who's in the back. Thank you for coming. Okay, so for our first part, the J. Modi Award. The J. Modi Award is presented every year to a computer science PhD student in honor of academic excellence and the potential to be a leader in the field. We have a number of great nominations for this award this year within the department, and it came out with, I think, an outstanding award selection. The award is going this year to Elsie May. Please come on up, Elsie. So Elsie is advised by Jeremy. If you can join us up here for a presentation. So Elsie is currently working on a thesis titled Automatic Library Generation and Performance Tuning for Exact Arithmetic. And he's received also a number of pieces of recognition in the past couple of years, including a couple of Best Poster Awards and some other things. So we're very excited about this, and in honor of his award, we have this outstanding College of Computing and Information and Informatics plaque for the J. Modi Memorial Award 2014-15. Congratulations. Thank you. We won't make Elsie give a speech this time. So on to our main event. In the past 6 years, we've had distinguished speakers from all over the country and the world, actually, join us for this event and give a number of outstanding talks. A lot of them had to do somewhat with AI and robotics, which was J. Modi's field of interest. Some of them not, but also outstanding talks. Today, we're honored to have not only a very distinguished speaker in the field, but also one of our close neighbors coming to us from the University of Pennsylvania. Dr. Vijay Kumar is the UPS Foundation Professor in the School of Engineering and Applied Science at Penn. His research, probably a lot of you know, spans many areas in mechanical engineering, computer science, electrical engineering. He's received many honors that I won't list through, but impressively things like Fellow of the National Academy of Engineering. He also served as the Assistant Director for Robotics and Cyber Physical Systems at the White House Office of Science and Technology Policy from 2012 to 2014. And last but not least, he is taking over as the Dean of Engineering over at the University of Pennsylvania as of July 1st. So we know he's extremely busy, and we're very pleased to have him here with us today to talk to us. Welcome, Vijay.
Thank you very much for the kind introduction. It really is an honor to be speaking at an event named after J. Modi and to be one of the J. Modi Memorial Lecturers. It's also a pleasure to be at Drexel. I've had former students in the audience, former research staff I work with, and a current student too who's here, who's working with me in the summer. So it's really a pleasure to be here, even though we're just across the street. Oftentimes these things are harder to do than to go to Japan or to Europe. So anyway, thank you for giving me this opportunity. So I want to tell you about some of the work that my students and I have been doing in the area of robotics, particularly swarms of robots and also aerial robots. And so that's sort of the title for this talk, and I should start by pointing out that the work is really being done by the people that you see here on the screen: Yash Bulgankar, Gareth Cross, Sekant Leary. These are current students. Giuseppe Loiano is a postdoc who's actually working on a joint project with Ani Sher as a professor here. Karthik Mota, another PhD student, Justin Thomas, also a PhD student, and Sarah Tang. And then many former students whose work I'll be talking about. So Alex Krishliev and Daniel Nellinger, who started K-Mount Robotics, which was recently acquired by Qualcomm. Matt Turpin is also part of Qualcomm. Xiaoji Shen is a professor at Hong Kong University of Science and Technology. Kaushal Srinath, professor at Carnegie Mellon. Katie Powers, who works at Beckman. So our interest in robotics is really motivated by applications in search and rescue. I showed here the two pictures that were taken from experiments we did in Sendai at Tohoku University shortly after the earthquake in Fukushima, where we sent aerial robots like this to explore collapsed buildings. And I'll say a little bit more about this work shortly. But not just inside buildings, but also outside. And you could imagine what works for search and rescue also works for first response and security applications. So these are, there's audio to this. Oh, there you can hear it. If I don't show the audio, it looks like somebody actually photoshopped these pictures, so I'd like to show this audio. So this is actually not too far away from here, unless you're from the FAA, in which case it's from Colombia. So we try to think about how we can use swarms of robots with downward-facing cameras that can respond to, for example, 911 calls, emergencies of all sorts. And the idea is that robots like this can respond much faster than human first responders. So by the time police cars arrive at the scene, robots could be at the scene, telling the dispatcher. And what you don't see here is the 3D mosaic that's built by all these robots, which is done on another workstation. But the dispatcher on the bottom right can see which robots are responding, how they're arranging themselves. He or she has no knowledge of which role individuals are playing, but can get situational awareness from the entire team. So we're also interested in applications in precision farming. So this is our robot flying in an orchard in Biglerville, which is about a 2-hour drive away from here, in an apple orchard. And basically what these robots can do as they fly through the orchards, between the trees and over the trees, is build models of individual plants. So a farmer can get a sense of the vitality of individual plants, what's the expected yield. And if you ask a farmer, and this may seem strange today in the 21st century, what's the expected yield of the farm? The chances of he or she are off by a factor of 2 or 3. It's just, they don't even know how many fruits are there and what their sales are likely to be that season. So using onboard cameras and LiDARs, you can build infrared maps like this. This is essentially an index that's built using a combination of infrared and visual imagery. And at the bottom right, you can see 3-dimensional LiDARs being used to construct 3D maps, which tell you where the canopy size will be. And you can see from the view of the robot, there are 2 other robots that are doing exactly the same thing. And if you want to cover large areas in a short amount of time, you might imagine lots of these being used concurrently. That's really why we need swarms in this case. So in all of these, the platform of our choice is a quad rotor, so a robot with 4 rotors, 4 propellers, each of which is independently controlled. And of course, in 2007 and 2008, when we started working on this, these were things we had to build on our own. But now there are lots and lots of companies building this for a fraction of the price that we could build it, but not as good. So we still build some of these in our lab. And you can ask why quad rotors, and I would argue that these are the simplest things you can build. Especially if you want to build a swarm, you want to build things that are relatively easy to build, so that you allow students to work on the really hard research problems, as opposed to figuring out how to build platforms. I think downstream, 5 years from now, you might see platforms like this, or platforms that are inspired by winged biological creatures, bats in this case, or mosquitoes, or bees. They have a lot more maneuverability and a lot more efficiency. But we're trying to bridge this gap in with rotorcraft. So here you see some scaling rules that apply for large rotorcrafts in the top right to really small ones at the bottom. You can see the picture of Yosh's hand and the robot on top. And then the smallest vehicle that's been built in Harvard, which is essentially a bee-like vehicle called the RoboBee. So this is a flapping wing vehicle. All of those are rotorcrafts. And if you look at the speed, which is the characteristic speed or the Mach number, which is obtained from the rotor tip speed, and the length, which is the diameter, you can see the scaling rule, which essentially tells you, and this is an empirical observation, but there's some physics that backs this up too, which says that the characteristic speed, that is how fast the rotor tip moves, goes to the square root of length. And this is, by the way, the same rule that governs roughly how we walk. So if I take two individuals with different stride lengths, chances are the velocity of the normal walk is roughly in this, follows this rule. So using this, you can actually show that your maneuverability goes as 1 over L. So in other words, your ability to accelerate in the angular direction goes as 1 over L. If I make a vehicle half its size, it can actually rotate or accelerate twice as fast, which intuitively makes sense. I mean, as athletes, the smaller the athlete, we know the more maneuverable the athlete is. The same thing actually holds as you build these, and that's one of the reasons why we try to build small aircrafts. So this is the smallest one we built, 11 centimeters, 20 grams in weight, 6.5 watts, at a maximum speed, which is about 50 times the body length per second. So if you look at a Boeing 787, for instance, that's like that plane traveling at Mach 11. So this thing zips quite quickly. But in addition to being maneuverable, it's also safer. And this is one of the reasons why. So in our lab, the first thing we realized when we started playing with these is we had to get first aid kits for their fingers. And if you plot a histogram of band-aids consumed over the years and sort of tailed off, with these things you can stick a finger in there and nothing will happen to you. So they're not only safe and maneuverable, but as you see from this video of honeybees, they're actually incredibly resistant to collisions. So when honeybees navigate individually or in teams, they don't worry about avoiding collisions like we think. In robotics, if you've ever worked in robotics, the first thing that you think about is how to avoid collisions. Because your robots are big, they're kludgy, they're expensive, and you want to avoid damage. Well, these guys don't care about it. So we want to build small vehicles of this size. In addition to being maneuverable and safe, we want to have these kinds of collision-resistant properties. And so here's an example of something. I think this is probably the first and only planned mid-air collision. And this video has been shot at 1/20th the frame speed, or slowed down to 1/20th the frame speed. So you can see these vehicles bump into each other, and they're able to recover from collisions based on onboard sensors, which are not too different from sensors that you find in the smartphone. So again, we try to build small vehicles, and we try to build swarms of these, mostly because individual vehicles have limitations at the scale, and by making lots of them, you can compensate for those limitations. So what I wanted to talk to you very briefly about is some of the technical meat that goes into this, and I group it into 3 areas. The first, although we think about how to write software, how to make these intelligent, underneath is some basic knowledge of mechanics and control that I'll try to share with you at a fairly high level. Second, the big problem, and again, you look at all commercial UAVs, most of these are navigated using GPS. We operate indoors, we operate in environments close to buildings where GPS often doesn't exist. So how to figure out where you are, how fast you're moving is actually not trivial. So this is the so-called problem of state estimation. And then lastly, how do you get lots of vehicles to collaborate, to behave as a single entity, and that's this problem of cooperative control. And by the way, if you have questions, please move it around me as we go along. I'd be happy to answer questions. So let's dive in. I want to talk about the first area, which is dynamics and control. So at a very basic level, what you're trying to control is the position orientation of this vehicle in some inertial frame. So you want to control a 3-dimensional position vector, and you want to think about the 3 angles, roll, pitch, and yaw. We prefer to use a rotation matrix because a rotation matrix doesn't suffer from the singularities that you get from roll, pitch, and yaw, but it's the same idea. So the main challenge is you only have 4 inputs, and the number of things you're trying to control is 6, 3 position and 3 orientation. So systems like this, and the control systems community, we call them unactuated. But fortunately, there are some interesting properties about the dynamics that you can leverage, which leads to very interesting motion planning strategies. So the property of interest primarily is a property called differential flatness. So the complicated story that I could tell you is that to model a vehicle like this, you need 12 variables, 6 position orientation, and then 6 derivatives. And the dynamics is ugly. You could describe it as on a manifold, lots of nonlinearities. Or you could think of this much simpler space, which is intuitively very easy to understand, consisting only of position and steering. So this is something we can kind of visualize in our head. So it turns out that any sensible trajectory you can draw on the right-hand side, respecting all the laws of physics, everything that we kind of know should work, but we don't have time to understand, actually maps into something, a smooth trajectory in this space, and the other way around. So instead of thinking of the hard problem of going from A to B in this very complicated 12-dimensional space, I need only think about the problem of going from A to B, the corresponding A and B in this space, making sure that my trajectories are sufficiently smooth. So the property of differentiability is particularly useful here. So therefore, motion planning reduces to planning a trajectory in just the 3-dimensional space plus this yaw angle. So that's the first simplification. The second simplification is how we control it. And I know that most of the people in the audience are computer scientists, so I'm going to keep this at a fairly high level and skip through some of the technical details. But let me just explain it at a fairly high level and say what we're trying to do is, armed with this description, trying to figure out what forces to apply, and then find out how to rotate the aircraft by applying the right moments to apply this force. So the first problem is figuring out what thrust. But remember, the thrust can only go in the direction of the propellers. What if you wanted to apply a thrust at a 30-degree angle to the propellers? Well, you have to rotate yourself. So this tells you how much thrust to apply. This tells you how to rotate yourself so that the thrust is in the correct direction. And it turns out this intuition is all that you need to make the controllers work. Armed with this F and M, you can then figure out what commands to send to the microcontrollers to rotate the propellers at the right speeds to get the right controls. And this is essentially the key piece of technology which runs at about 600 hertz to 1000 hertz, depending on which processor you use, that allows things like this to happen. So here you see Daniel Ballinger throw this robot into the air and it recover. This is the smaller vehicle I just showed you bumping into into pillars with or without that cage. The cage is meant to protect the propellers, but in some cases, even collision with propellers is safe, as you can see. But all of this relies on this very, very reliable, robust controller that's just keeping track of position and orientation. So this is the lowest level of software. And then an immediately higher, superior level, you want to think about the problem of planning, which I talked to you about earlier. And again, imagine you have to go from A to B. Imagine there are obstacles. Because you're planning in this space, which is only 4-dimensional, I can leverage tools in computational geometry and keep the problem at a fairly simple level, because once I plan it here, and remember, I have to plan sufficiently smooth trajectories that avoid obstacles, then I can transform it back there. So the question of what trajectories to use is also an interesting one. The temptation is to use shortest distance paths, but here you have to respect the dynamics. And we use a functional which is not quite based on distance, but it's based on a higher derivative of position, which is called snap. So if you take position, you differentiate it again, you get velocity, then acceleration, and then comes jerk, and snap is actually the fourth derivative. You can go higher, snap, crackle, pop. Actually, it turns out snap is really what you need to make all of this work. So I'm going to just show you a couple of videos that illustrate how planning in this flat space, space that's easy to understand, actually generates fairly complex trajectories in that more complex space. So here's the first one, which shows how the robot goes from A to B, but going through an intermediate point C. And this is in slow motion. The thing you want to remember is although this vehicle is rolling and pitching, the trajectory is actually planned in this XYZ in your space. There's no roll and pitch when you plan trajectories, but when you transform it, you automatically get that roll and pitch that's needed. So this can be done really quickly, 10 to 100 times a second based on, again, what processor you're using. And then the question of can you get this trajectory to go around or through obstacles can be easily addressed if you know where the obstacles are. So this is showing you the ability of the robot to go through hoops whose positions it knows. And in fact, these hoops don't have to be stationary, they could be moving. And as Daniel Manager throws this hoop up in the air, the robot essentially predicts where the hoop is going to be and then calculates the trajectory through this moving obstacle. And again, you can do this because the underlying planning algorithm is a quadratic program that we can run quite quickly using off-the-shelf solvers. And it works not just for navigation, but for a few other tasks as well. I want to show you some work by Justin Thomas and Kaushal Srinath that shows how we can do things similar to this eagle, coordinate eyes, arms, wings, and feet to fish. And here's a robot going after, it looks like a Philly cheesesteak. But essentially coordinating actuators along with sensors that tell it where the object is, and grabbing an object out of thin air, going at speeds of 3 meters per second. So to give you some sense of speed, 2 meters per second is roughly walking speed, so it's a little faster than walking speed. So everything I've shown you thus far, are there any questions? I know I've gone through this pretty quickly, and I'm happy to answer questions that I mentioned earlier.
Cheesesteak delivery service?
We could do that. If there's a business model, let us know. But the one thing for those of you who are familiar with some of this technology you should notice is that we actually cheat here. So this robot actually has no sensors on board. All the sensors are off board. There's a bank of motion capture cameras that's calculating the positions of these reflective markers 100 times a second. So as a result, it broadcasts this information to the robot, and it knows where everything in the environment is once every 100th of a second, every time in seconds. So the example, we throw the hoop into the air, you take a snapshot, next time it falls, it's probably moved, well, I don't remember how much it's moved, but you get about 3 snapshots, 10 milliseconds apart, and then you have to extrapolate and then figure out how to get the trajectory through that hoop. But the problem of perception, reasoning about the environment, is almost trivialized with this kind of experimental system.
So how many outtakes do you have from that example?
If you have time, I'll show you some bloopers at the end. But it turns out that the model and the little bit of iterative learning we do to improve on the model is shockingly good. So the outtakes we get is more about how the human threw the hoop and also about breakdown of wireless communications. Because as I'll show you here, let me tell you a little bit about the software, I'll tell you what things are likely to break and what are not. So we have this hierarchical controller, and if you look at the innermost loop, it operates at roughly 1 millisecond. The loop in between is 10 milliseconds, the one outside is about 100 milliseconds. The thing that's most important that works quite robustly is this onboard control. So this is completely independent of any external sensors, any communication. But after that, what I've shown you, the robot relies on external motion capture cameras to calculate position or vector and its derivative. And the trajectory control is done on a laptop similar to my MacBook here. So the laptop has to talk to the cameras and then the laptop has to talk to the controllers on board. And all of this happens over 2.4 gigahertz. So if somebody walks in with a cell phone, turns on a microwave, or as we discovered recently, with these RF microphones that TV reporters like to use, that interferes with all of this, and we drop packets, and then that's where things start to go. But again, this is where we test our algorithms, this is where we prototype things, and include videos. But in reality, you're not going to have any of this. In fact, the most impressive aggressive navigation was demonstrated by Northrop Grumman with this X-47B, where they showed unmanned landing on a moving ship deck. But this is using military-grade GPS and extraordinary communications, so they cheat too in some cases. And all I can say is that our lab costs taxpayers a fraction of the money that this costs. But the real problem is, even outdoors, this is next to our lab, it's very hard to get the GPS, and certainly inside you can't get GPS. And so this question of onboard state estimation is a big challenge. So I want to just share with you some of our work in this direction. But all of our work assumes that we have a robot like this. So this robot is considerably bigger. It carries on board a laser scanner. This is that orange thing you see on the top. And then the two cameras sitting at the top, and then GPS on top of that, which is optional. And then there's a downward-facing camera that you don't see, which looks down at the ground, and then there's a pressure altimeter that tells you the pressures. And of course, we have an IMU, somewhat better than your smartphone-grade IMU, which it needs for navigation. So how does this work? Well, the technology that's really become quite mature in the last 10 to 15 years is something we call SLAM, simultaneous localization and mapping. So for those of you who don't know, this is just a really quick overview. So imagine you're X0. You don't know where X0 is, but this is where you are. And imagine you can see a bunch of features. So if you have a laser scanner, these features might be reflections of anything that I see in the wall that's giving me a return. So it could be the walls, it could be the pillars, and so on and so forth. Not the glass windows, but everything else, pretty much. If it's a camera, it could be changes in intensity, changes in gradients of intensity, sharp color contrast, and so on. And so at any point, you make these observations. So each of these green arrows denotes an observation. So you take a step to X1. You make a few more observations. Perhaps the features you see now are a little different than the ones you saw before, and so on. So as a result, now you have a graph. So this graph consists of two types of edges, the green edges and the black edges. So the green edges are all observations, and they're all typically quite noisy, because remember, we're trying to make this really small, so we are less likely to use the expensive lasers, the expensive cameras. So these are noisy measurements. And then these black edges are essentially edges that measure how far you've gone based on onboard sensors like IMUs. So if you have an inertial measurement unit, you can estimate how far you've gone. So the semantics of these edges are different, but they all contain quantitative information. So now you can imagine this gigantic optimization problem that you could solve, which allows you to recover the positions of X1, X2, and X3 relative to X0, and the locations of the features relative to X0. So this is sort of a SLAM problem. We basically have to solve this in real time in order to get the robot to work. So this is sort of the key box, the key building block. But let me also show you what really makes the thing work. Again, if you go back to the bottom right, I told you we have a great controller that runs at 100 hertz. The thing it needs in order to work is an estimator that feeds in position velocity information reliably at 100 hertz. So we use something called an unstunted common filter, which is a variation of a common filter, which is at least 55 years old. But this now allows us to use a whole bunch of sensors, so GPS edge cameras, pressure altimeters, stereo cameras, a down-facing camera, the IMU, each operating at different frequencies, and each with different noise characteristics. So we're able to combine these using models of the statistics of the noise and then yield an output that's something that a controller can robustly act on. So I want to show you a couple of examples. The first one illustrates the problem that Amazon has to solve when it thinks about package delivery, and this is work by Xiaoji Shen, which shows how the robot can actually navigate features that are close to the ground and close to trees and buildings. Again, the package delivery problem, going from point A to point B is not hard, but it's landing at A or taking off at A and landing at B that's hard. So this is basically showing a whole bunch of sensors, depending on the color of the ellipsoid, that tells you the uncertainty of that particular pose estimate. The bigger the ellipsoid, the more the uncertainty. And by the way, the ellipsoid looks really big, it's because it's scaled by a factor of 100. But again, green here means it's using just its vision laser because GPS has failed. If it goes out in the open field, it will only use GPS. If it's inside buildings, as you'll see in a minute, and if it's dark, like right there, the only thing that it really uses is a laser. So it combines these different pieces of information as it flies, and this is probably the longest flight we've done in a mixture of indoor and outdoor environments, lasting about, it's about half a kilometer long and going at about a speed of 1 to 1.5 meters per second. So this is the problem that's really hard, which is, you know, the Google car often navigates by knowing exactly what the map looks like. Well, if you're low to the ground, if you come back right at this corner, that tree would have grown, and it's no longer the same as the last time I saw it. And Google Map updates are not as frequent. So if you really need to operate robustly in a changing environment present with humans, you need to integrate packages like this into small form factor UAV. And this is one of the challenges. But once you can do this, and this is work by Sikong Liu, you can actually get really high accuracy maps. So this is an indoor map built by UAV, and this has been sped up 4 times. You'll see it build maps. This is outside our lab. In a minute, you'll see it enter our lab, which is instantly recognizable with all the junk lying around right there. So that's our lab. And this map has is at a 5 centimeter resolution. And you can see the accuracy that you get is much better than what our floor plans will tell you. So something like this could actually be used to map structures like this and build drawings of legacy structures, for example. But what we want to really use it for is, again, for search and rescue. You can imagine robots like this being sent in and exploring completely unknown environments and telling remote user what's inside that environment. But there's one problem with this. So I told you we want to build really small robots. Something like this weighs close to 2 kilos. And this might be hard for us to understand, but robots like this consume roughly 200 watts per kilo. Right? So to put things in perspective, if I can take the most athletic of you and put you on a treadmill running at max speed, you probably will consume about 2 watts per kilo. So we're about 100 times more inefficient than you are, and you could say, well, let's put a better athlete. You can take Usain Bolt running 100 meters, so he consumes about 20 watts per kilo. So we're 10 times more inefficient than Usain Bolt. And this is the primary reason we want to make things really small. Not only do you want to make them small, safe and maneuverable, but you also want to make them practical. Because remember, they're running on roughly the same batteries that you see in your laptops or your smartphones. So the question we asked is, well, what kind of a device can we buy that's inexpensive, lightweight, and contains sensors and computers on board? And the answer is your smartphone. And so we asked ourselves, can we build everything on a smartphone? So we invented what we're calling the flying phone, or the phone. And so this vehicle, everything here is off the shelf, except for our app that runs on the Samsung Galaxy smartphone, which is off the shelf. And you can see this robot doing pretty much the same thing we were doing with the motion camera system. Navigating at speeds of up to 2 to 3 meters per second, rolling and pitching at angles of 30 to 40 degrees. doing exactly what I told you before, the SLAM algorithm with the UKF filter, but now everything runs on board the smartphone. So this is great from so many perspectives. The first, the consumer electronics and robotics are a collision course, which means we can leverage everything we've all paid for. Right? We're the ones that made consumer electronics affordable, and finally we can now go back and get the benefits of that. But the other thing is, of course, that now you can see that a lot of the consumer electronics companies, companies like Qualcomm, for example, are heavily investing in robotics because they see that's where they see the future of all the hardware and software that are built. So this is, Adam Cho is here, is working on a version of this with a different phone. So we're trying to make this so that at some point you can buy the robot or the drone from a company in China for a fraction of the cost that we make it. And you can buy a Samsung phone, and you know how much you pay for a Samsung phone. And all you need is the app that you can download from an app store. And you don't need GPS, you can navigate indoors. So that's the whole idea of this. Let me pause and see if there are any questions. Yes?
Quick question. So the outdoors one, were you actually using stereo to back out? So the laser is a one-dimensional scan.
So we're not doing stereo. It's not to say we couldn't, but remember, for just like in this case, for just figuring out where you are relative to features, you don't need to reconstruct the environment. So the software here just uses the camera that comes with your smartphone and the onboard IMU. And by the way, that IMU is dirt cheap, and therefore it's actually a lousy sensor. The camera is actually a lot better because we take pictures of it, and that's the saving grace. It's what we all want in a smartphone that actually makes this work. Completely different application. But there is no stereo. Yes?
I'm sorry, so you're saying the accelerometer on the phones are not of high quality compared to what you need?
No, in fact, we started working with the iPhone 4, and the iPhone 5 is worse than the iPhone 4 because they figured out how to cut costs on whatever the 2 cent thing, now they're replaced with the 1 cent thing. So,
Just one of the follow-ups would that be that if you have a good accelerometer, basically a gyro, you can now use optical. Even if you just have a stationary optical source of some type, you have need some reference to do a quick calculation and know you're already doing.
well, I'm not quite sure I understood the question, but let me just make one comment, which is if you have a really expensive IMU, like all those black submarines that navigate under the black meaning classified, they're actually black in color, that's a different issue. Which navigate under the polar ice cap, they navigate based only on dead reckoning. They're able to integrate forward. But that I don't know how much that costs, but that's outrageously heavy from our perspective and expensive. So you have to balance it with some other kind of sensor, and vision turns out to be the best thing. Of course, in a dark room, this is not going to work, or in a smoky room, this is not going to work. And hence the reason, if you really want to make a future of package delivery or delivering hoagies, you might think about a variety of sensors that work in several environments. Yes?
The laser sensor is on top of one, so it's about 2 kilos. Is that a single LMS sensor?
No, it's not 2 kilos. Actually, the laser is only about
The whole unit is
Oh, yeah, it's
the
yeah.
actual specific laser sensor.
It's made by a Japanese company called Okuyu.
Okay, and alright.
I mean, both Okuyu and Velodyne have lightweight 2D and 3D sensors. So this one is Okuyu. Yes?
So for the navigation, were you taking them into account? So like moving obstacles like a person in your navigation?
In everything I showed you, there were no human obstacles, but I mean, we've done that too. So it's not too hard to map. Well, we map obstacles, that comes for free. And then the question is, when you plan trajectories, can you go around obstacles? So the only trick with humans is there's this unfortunate property that they actually move. So then you have to essentially keep updating your map and then discard things that have changed substantially since the last time you measured based on time. And that's how you model dynamic obstacles for the humans. Okay, so let me move on to the last piece of my talk, which is really now how do you build lots of robots and get them to collaborate. And again, I want to focus on one aspect, which is related to getting them to move as a group with one set of instructions being used to command the team or the swarm. So one of our first experiments with flying robots was a construction experiment. This is done by Quentin Lindsay, who's now working for Air Environment. So this is a problem where we took truss-like elements, and each truss-like element had a magnetic fastener, so the construction, the fastening problem is trivial. But robots had to figure out which robot picks up what piece from where and assembles it at what point in the particular construction project. So the robots have the same information. They're given a CAD drawing of what the structure needs to look like. The rest of it is automated. They're negotiating with each other, trying to figure out what part of the free space is available for planning, and they're simply determining who picks up what part. Now, this is collaboration, but it's in small teams, and that's an important thing to note here, because if you look at this problem, if you have 3 people collaborating, 3 pairwise conversations ensure that the complete picture is available to everyone. It's not true when you go above 3, right? So if you do only pairwise conversations, there will be one conversation that will never be had in every set of conversations. So this works for small teams. The more general problem, however, scales combinatorially or at worst exponentially. So the first problem is the so-called labeling problem. So you've got robots at S1, S2, and S3, and the question is who picks up what parts, and let's say the parts are the locations named labeled with G. So you have to essentially say, well, that's G1, that's G2, and that's G3. So you're labeling. And as you might imagine, that goes as n factorial and vehicles. So the assignment problem is essentially determining the assignment of robots to goals. The second problem is a trajectory planning problem. So this is tricky because you can't do it one robot at a time. And the reason you can't do it one robot at a time is because you want to guarantee safety. You want to make sure that these robots don't come too close to each other. So that's the safety question. And then finally, if you obsess about things, if you want to write a good thesis, you have to think about optimality, right? Although in this case, optimality is not a big thing, but it's something to try and do. And so the first problem and the second problem can be solved independently, but we try to couple it. So this may seem a little paradoxical because the first problem grows as n factorial, the second problem grows exponentially with the number of robots. And the last thing you want to do is take 2 difficult problems and say, hey, let's combine it and make it even more difficult. But paradoxically, it turns out that if you combine that, things become simpler. And I'll tell you a little bit about that solution, which turns out to be only n cubed complexity. But the real fact is that if you look at nature, this picture is a little washed out. These are pictures of starlings off the coast of Denmark. There's a million starlings, and they form these incredible shapes. And they're not thinking about goal assignment or planning trajectories or collision avoidance. They just do it. And so one question we can ask is, how does nature form these kinds of incredible patterns? And if you're not interested in patterns, there are a number of things that nature does just for survival. And I'll give you 2 examples. So this is ants forming bridges to get from an area that's flooding to a dry area. And they form these bridges spontaneously. So this is an example where my former student Spring Berman, along with Stephen Pratt, a biologist at Arizona State, are studying ants where they learn how to cooperatively carry large objects. And here the question is, so the reason they're carrying this acrylic object is because the acrylic object is being coated with the juice from fig, from fruit. And because of that, they think it's food, carrying it back to the nest. And the idea is you can look at robots that are pulling by the deformation of the structure, robots that are pushing, and then robots that are kind of goofing off on the side, not doing anything. So you can see which robot is doing what on this kind. But the key thing is this kind of cooperative prey retrieval mechanisms encoded in ants, in these particular desert ants. So how do they determine which robot does what, and how do they figure out how to move? And this is a question you can ask for birds, for ants, for any kind of collective group that you see in nature. So rather than study biology, we can ask as software engineers what kinds of principles can we take away from this in order to architect software systems for swarms. And I want to just share with you three basic ideas. So first is, you've got to make sure that you don't rely on everybody being connected and some central agent commanding all of them. Each one has to act independently. And when you do that, it's inevitable that in a large team, someone at the bottom here has no knowledge of what this person is seeing, right? So it's relying on you to know about information. And then lastly, this is something we don't think a lot about, is you can't have your formulations depend on the identities of specific individuals. You have to operate in this paradigm of anonymity. Individuals have to be agnostic to who their neighbors are. So this is not unlike, if I were to ask any random sampling, 3 or 4 of you to carry, I don't know, this furniture out of the room, I bet you don't have to know each other's identities or your work habits or your play habits to actually do this, right? So that kind of anonymity needs to be preserved as we think about formulations of these kinds of formation control problems. So there's a lot of literature in this area. Let me share with you 3 ideas, 2 of which work for our setting. So the first idea is that maybe all you need is you have one leader that knows what to do, and everyone else kind of maintains appropriate relative distances and follows that leader, and as a group they can do something akin to what you saw earlier. So this is the first idea. It turns out that this is quite brittle, because if I shoot down the leader, the whole team essentially disappears. So the second idea is that we do this without leaders. And here the key idea is that every individual listens to its neighbors and then performs decisions based on what that neighbor is doing. So a simple manifestation of that is the so-called consensus algorithms. So if I ask all of you to compute, think of a single number, and I only allow you to talk to your neighbors, you can come up with very simple averaging schemes that ensure that we all come up with the same neighbor by just talking to your neighbors. So that's the same idea here. And I think democracy works roughly in this way. Another idea, but the problem with this, by the way, is that you don't, like democracy, you don't know what the outcome is going to be, oftentimes. So to know a priori what that average is actually quite hard. So another idea is to have what I've called leaderless aggregation, but with wanting to ensure that a prescribed distribution is achieved. So for instance, I want all the robots to be in a circle, or I want them all to be in this incredibly beautiful swarm shape. And this is something that Ani Sheo, sitting in the back, did her PhD on. So this is kind of a key idea that we have absorbed into our thinking as we think about aerial robot swarms. So I'm going to illustrate the 3 organizing principles using some very simple videos. The first one illustrates this simple idea of leader-follower networks. And here the leader happens to be a human being who has just hijacked one of the robots, literally. And you can see that because the robots are talking to it, as the leader moves, all the other robots follow. It's done purely by communication. Every robot is relaying to its neighbors what its position is, and they're trying to maintain a given formation. So in this particular formulation, it turns out that you can have multiple leaders, but in the particular video you see here, there's only one leader. And despite all the theatrics of David Pope, they're not listening to him, they're only listening to the robot that he's carrying. So this is one key idea. The second key idea is this notion of anonymity. So in anonymity, the idea is that now they're maintaining a circular formation. Matt Turpin's work. But regardless of how many robots are there and who these robots are, they essentially figure out a way to maintain spacing and essentially form a circular pattern. And here again, they're solving what I call the concurrent assignment and planning of trajectories, the so-called CAP problem. And remember I told you that the coordination of large groups is a problem because it grows exponentially. The assignment problem goes in factorial. But if you actually combine these two things, there's an order n cubed solution, which Matt came up with. So now, back to the problem with the Starlings, if you put these ideas together, you can actually change the shape of the group and the rate at which it moves dynamically based on a single set of mathematical equations. So those equations essentially describe the shape of the group and how it needs to change as a function of time. And the robots essentially figure out how to take these different positions on their own without Matt actually specifying how many robots need to be in the team and which robot needs to do what. So this is important because, again, it allows one person or a single set of instructions to command this entire team. And once you do that, you can also react to changes in the environment. So this essentially shows a team of 20 robots, but now if there are obstacles in the environment, they can actually reconfigure to go through obstacles. So this is just showing a replica of shapes, and soon you'll see them trying to go through that window, which is off in the corner, so right here. So you can actually think about how to change the formation to go through this. But again, why are we doing all of this besides making cool videos? The real thing we want to solve is that search and rescue problem that I told you about earlier. So I want to go back 4 years, almost to the day, to this experiment we did in Sendai, where we essentially borrowed one of the robots from our Tohoku University colleagues. This is the ground robot you see here, our aerial robot sitting on the top. And by the way, our robot is programmed to hitch a ride whenever possible because it's starved of energy. So in order to conserve power, it's essentially sitting on top. But when the team gets confronted with this collapsed doorway, or the ground robot releases the aerial robot, which takes off. And both robots are constructing these 3D maps, and you can see this happening in real time in the bottom right panel. So together, we're exploring this environment. So in this particular video, you can see our robot going over that bookcase and looking at the area on the other side, which is actually would have been hard to do with a human. And certainly the ground robot couldn't even enter that area. So you'll see this team systematically explore their collapsed electrical engineering building, which we did the 7th, 8th, and 9th floor, and laboriously construct a map like this. So this is a 3-story map, and it took 2.5 hours to construct this map. And again, no first responder or search and rescue worker is going to give you 2.5 hours to construct maps like this. You'd be lucky if they give you 2.5 minutes. We'd like to do it in 2.5 seconds, actually. And that's where the special response come in. So we want to take sensors like this, algorithms like this, but think about how we might apply it to smaller systems, and then allow them to coordinate their motions, and not just do formations, but to actually do useful tasks like this. And that's really where we're going. So I wanted to close on a light note. I wanted to show you a video that's been created by my former students who were at KML Robotics, along with the Lexus Motor Company. I don't know if you can see this. Can you turn up the volume, please? So this is just a 1-minute clip. It's a fun clip. So let me just conclude with a poster of a movie that's coming nearby, Swarm. So I love this poster. Have you seen this movie, by the way? If you haven't, don't see it. It's a terrible movie. I love the poster because everything about this is true. The size is immeasurable. The power is limitless. I hope you agree. Even this last bit is true, although politically I would say its enemies, the human race, because I think the technology is here, and the question is, how do we leverage this technology to do something useful? So even that last bit is true. Thank you very much.
We have time for one or two questions. If anyone has them.
I'll ask. How much is battery? I mean, you're talking about great technology, but ultimately these things have to be powered. I mean, obviously maybe the solar cells during the day, but it almost feels like you're doing great work, but someone still needs to be pushing on battery technology.
It's a great question. If you look at lithium polymer batteries, which is really where we are today, maybe you'll see a 5% improvement, and when that happens, all the battery guys will be on the rooftops shouting, "Yeah, look at what we did!" And that 5% is not going to change what we're doing. So you're right. I think in the next 5 years, I don't see any big, boost in technology coming through in that. But let me turn that around and motivate why you need swarms. Because if you have small batteries, you're going to have missions that are going to be shorter. And you have missions that are going to be shorter in time. You want to have robots that are faster and smaller. And if you want to cover large areas, that's where you need swarms. So in some sense, that is one of the reasons why we're forced into this way of operating. And there are lots of interesting, I think, missions requiring this up-tempo operation. And first response and search and rescue is just one of them.
Following on that, all of your robots tend to be the same. There's not a staging in there of like some of the robots will carry power sources for other robots.
Yeah. So you're absolutely right. There's a whole dimension to this which can exploit heterogeneity. We haven't done this per se. This is one of the aspects of this project with Ani, where we think about how we can use ground robots, swarms of ground robots, and aerial robots. There's a natural synergy there. But, so I just try to demonstrate one axis where we're going to push the technology. Yes.
Do you find there's an inefficiency as you get smaller because air molecules stay the same? When you have a large model, it's easier sometimes to plan propellers as you get smaller. Does it change some of the models?
Yeah, that's a really interesting question. So as you get smaller, you invariably get noisier. Things behave less predictably, but not in the way you would think. So for instance, if I take like a Black Hawk helicopter, and what I know about its landing is very different from a small robot landing in a chair. Because that would be analogous to the Black Hawk helicopter landing next to a large cliff or next to a canyon. So these small features, which to us don't seem like much, tend to create a lot of interesting aerodynamic effects. And because of that, the stochasticity is significant. And that means you have to work harder in terms of building a robust software. There's something which is completely paradoxical, or not paradoxical is the wrong word. Let me just describe it to you. So it's something called a ground effect. So the ground effect, if you've landed in an airplane, you've seen it, right? So the good pilot, you always try to take one side of the landing gear and try to make sure it makes contact as soon as possible, because the ground is pushing back on you because of the aerodynamics, and that part of landing is the most dangerous. So you want to land as quickly as possible, and so the pilots will oftentimes just roll the aircraft so that the right side usually gets down first because the ground is pushing back. So we experience this. But what pilots never experience is the opposite of this, which is the ceiling effect. So you're traveling close to ceilings, which we do, and we found out the hard way, you get sucked into the ceiling. So that's an example of something that only because you're operating at a small scale in human-built environments, you run into those kind of problems. Yes?
Have there been any attempts to kind of combine some of the mapping, the three-dimensional mapping capability that you have with a smaller scale of quad rotors that run off?
And that's what we're trying to do. This is what Adam is working on. But again, people, users like you and me, want more and more power on phones. We no longer want to just take pictures and videos. We actually want to capture things in 3D. And that's great news for robotics because the integration that companies like Qualcomm are going to put in their chipsets will actually benefit us. We're actually working with Qualcomm on exactly this. So we'd like to be able to take that Samsung Galaxy smartphone and build 3D models of that.
Thinking back toward what you mentioned toward the beginning of your talk, referencing some of the sort of unique capabilities of metals, and thinking of them as sort of these highly evolved autonomous agents. Clearly, they're not using sort of commodity products. They're using products that they're platforms that have been very carefully sculpted. But I gather from your talk that you think that much of the potential right now is in leveraging what is available as a commodity. Can you talk a little bit about sort of what we're at?
Yeah, so this is partly my taste in research and partly strategic. If you want to build a swarm, you can either try to work on the swarm or work on the individuals that constitute the swarm. So you don't want to put a critical research problem down another one. Having said that, I'll also say that some of the more advanced designs are just ideas. So remember, for autonomy, you have to take that idea, you have to fully understand it to the point you can build it, and then you have to kind of invert the idea. In other words, you have to invert, so in thinking about physics, if you understand the laws of motion, that's good, but you also have to figure out how to invert that law of motion to figure out what forces to apply to get the desired motion. That's extremely hard in flapping wing aircraft, for instance, because we don't understand the non-steady fluid dynamics and all these other partial differential equations we never understood anyway. But those are one of the problems that I think we end up. Not to say it won't happen. But in the immediate future, I don't see that as it.
What should a student do to join your lab? Like, what kind of qualifications do you expect?
We have fun.
No, what kind of qualifications do you expect a student to have in order to join?
I think it's a mix. I think you walk into my lab and you'd be hard pressed to say this person is a computer scientist, this person is an electrical engineer, mechanical engineer. So I think, Da Vinci was a Renaissance man. I think this field is growing towards Renaissance men and women. We tend to specialize, but increasingly these kinds of things are systems thinking. You need systems thinkers. People who are not uncomfortable about, picking up a soldering gun and doing some circuit board assembly, or going to a 3D printer and making a physical prototype, or writing code in whatever language. So I think it's a mix of skills. But for a doctoral thesis, you have to be laser focused on a particular problem, and those tend to be very heterogeneous. Those depend very much on the individual, where he or she wants, which department he